We'll talk more about what that means later. So anyway, we're going to talk about calorimetry and phase change. For some of you, this will be a review, so we'll go through it sort of quickly. What are the phases of matter? You can read them. Yes, solid, liquid, and gas. Those are our phases of matter. And solids have a definite shape, definite volume. Molecules don't really move. What can molecules in a solid do? It's kind of like jiggle. Okay, that's all they can do. Liquids have a definite shape, but it's the shape of whatever container they're in for the most part. They have a definite volume because they don't really expand and contract easily. And the molecules are held together, but they're more loosely bound. So they have lighter bonds between them than a solid, okay? A gas, molecules move about freely. Now in physics, both of these things are considered a fluid, but there's a pretty big distinction between how a gas behaves in thermodynamics and how a liquid behaves, okay? So let's talk about what happens with heat transfer. So let's say we have a temperature versus heat graph, okay? So let's start with, I don't know, something like simple. Let's start with water, okay? So let's start with solid water. As we add heat to the water, what happens to the temperature of the water? It rises, okay? And what should the slope of this be, or what should it have to do with? MC, yeah. Well, in this case, it would be 1 over MC because heat is on the x-axis, but it's related to this. Remember? This has to do with our slope because we're relating this and this, and we know they're linear. Does that look linear? Okay. Now let's say we get to the melting point. Right? When it melts, yeah, it stays constant. Okay? Which means we're still putting heat in, we're still putting energy into the system, but what's happening to the temperature? It stays the same. Okay? Which means that does this equation work for this? No. Because if you look at this, delta T is always going to be what? 0. Okay? So this is a temperature change, this is a phase change. Q is different for phase changes. And then, of course, this becomes a liquid, right? Until you get to the boiling point. And then you have another phase change. And then it becomes a gas, and you can heat up the gas. Okay? What this says is, like you, I assume, have had a glass of water with ice in it. Yes? Once the ice, at the point where the ice starts to melt, the water and ice end up being about the same temperature over time. That's your zeroth law, right? You have thermal equilibrium. But you can have water and ice both at 0 degrees, okay? If you go above 0 degrees, then everything becomes water. If you go below 0 degrees, everything becomes ice. But you need a certain amount of energy to do that phase change, okay? And here's your slope. So it turns out the phase change is given by this formula. So the heat it takes to change phase is this. And this is just m, which is the mass, times a constant that has to do with the material. All right, and all these constants will be given on a test, but I just want you to know which ones are which. This is the latent heat of fusion. What does that have to do with? Which phase change? Liquid to solid, solid to gas, liquid to gas, solid to liquid, or liquid to solid, back or forth. How do you know if you're going one way or the other? The sign, okay? Because remember, when is heat positive? Going into the system. When is heat negative? Coming out of the system. So if you have ice and it's turning into water, should this be positive or negative? Positive, because to get ice to turn into water, you have to add heat. Heat goes into the system, so Q is positive. If you have water that's turning into ice, negative. Okay, you have to pull heat out of the system in order for it to freeze. All right, this one's called the latent heat of vaporization. So that's liquid to gas and gas to liquid, depending on the sign. Okay, if you have a liquid and you want it to be a gas, is Q positive or negative? Liquid to gas.
Positive.
Positive, right? If you have water and you want it to be steam, you have to add heat, okay? If you have steam and you want it to be water, you take it away. That's condensation, okay? So, yeah. Anyway, that's that. So we have two ways of figuring out heat, right? We have temperature change, but we also have phase change, all right? And here's a fun chart that you don't need to memorize, but it's always nice to have as a reference for different materials. This includes their melting point, the latent heat of fusion, boiling point, heat of vaporization, okay? So you know that these phase changes only happen at these temperatures, okay? Because if you have water, let's say you have, well, let's do it. Let's say you have water at negative 20 degrees. What do you have to do before you get to a phase change? Or sorry, ice. You're right, ice. How do we get the ice to a point where we can melt it? Heat it up. To what temperature? 0 degrees. Okay, so let's walk through this. Okay, and this is this is the kind of stuff you can expect to be given to you. Okay, so you don't need to memorize a bunch of constants, but you do need to know how to use them. Okay, if I give you the chart, know how to use it to do the problem. So here we want to know how much heat is required to change 200 milliliters of ice at negative 20 degrees Celsius, which is apparently a typical freezer temperature, into steam. Okay? So what's the first problem you see with this?
Gas.
So before we even do MC delta T, which is the first thing we have to do to get to a point where we can melt it, what's M? Yeah, milliliters is a volume. Okay, so you can't use that as M. How do you get from, yes?
You use density.
Yes, you have to use the density. Okay, because remember, volume mass density is mass over volume. We were given volume, so we need to do this. Volume is, we need mass, sorry. Mass is rho times volume. Okay, and just fun fact, a milliliter, so we have our density in kilograms per meter cubed. So this is 920 kilograms per meter cubed for ice. How do we get the volume in meters cubed? So milliliter it converts to centimeters cubed, right? 1 to 1 if it's water. Close enough for ice. So this is 200 centimeters cubed. But we need it to be meters cubed. This is in cubic centimeters. How many cubic centimeters are in a cubic meter? Do not say 100. How many centimeters cubed are in a meter cubed? Yeah, 1,000,000. Okay, do you want to know why? So if you just have one-dimensional things, like a length, okay, 100 centimeters is equal to 1 meter. Okay, if you want cubic centimeters and cubic meters, you cube stuff. Now that's no problem for this one thing. That's 1 meter cubed. But this becomes 100 cubed centimeters cubed. Okay, so this is 1 times 10 to the 6th centimeters cubed is equal to 1 meter cubed. Okay, when you're dealing with volume, it's cubed. Not just the units, but the values next to the units. Okay? So 1 meter cubed has 1,000,000 centimeters cubed in it. Okay? 1 meter has 100 centimeters in it. But 1 meter cubed has 1,000,000 centimeters cubed in it. And people fuck this up all the time. Do not let that be you. Okay? All right. Which is the only reason I put this in this problem, because I want you to see it before a test. Okay? Because it's just such an easy conversion if you know what you're doing. All right? So this becomes how many centimeters? So 1 meter cubed over 1 times 10 to the 6th centimeters cubed. Okay? And so when you actually do this out, you get something like 0.184 kilograms. Okay? And now we have our mass and we can begin. to the actual problem. All right. So we're going to have several stages. So if we start with ice and it's at negative 20 degrees, first we have to warm it to 0. That takes an amount of heat. That's a temperature change. Then what? Then what do? We add more heat to melt the ice, right? So we raise the temperature, then we melt the ice. So we have an MC delta T, and then we have an ML, okay? And then you have water. But does water just boil when it's at 0 degrees? Nope. You use MC delta T again. You heat it to 100 degrees. And then you have to use another ML to get it to change phase from water to steam. So there should be 4 Qs, and the total heat you need is the sum of all 4 Qs. So Q1 is M ice, C ice, delta T, okay, which is 0.184 kilograms. The specific heat of ice is 2090 joules per kilogram Kelvin. And the change in temperature final should be what? 0 minus negative 20. So that's 20 Kelvin. Okay, so 0 minus negative 20, positive 20. Which makes sense because you're heating up ice, which means you're putting heat in, and Q should be positive. Okay, so that's going to give us 7.7700. That's 8,000. So 7.7 kilojoules. That's about 7,700 joules, or 7,700 joules. Okay, so not a ton of heat. Q2. Now we have ice that's 0 degrees. We need it to be water. So we use math. And which latent heat? Fusion or vaporization? Fusion. We're going from a solid to a liquid. Is it positive or negative? Positive, we're putting heat in to melt the ice. Okay? So we have the same mass, 0.184 kilograms. And why do you think it's mass? Do ice and water have the same volume? No, right? The density changes as you go from ice to water. But you know what doesn't change? The mass. Okay, because the amount of molecules is still the same, they're just structured differently. Okay, and mass comes from the individual atoms. So, then we use the latent heat of fusion. That's going to be 3.33 times 10 to the 5th joules per kilogram. Okay, which means the second heat, the heat we need to melt the ice, that's going to be 61.3 kilojoules. All right, so heat ice, melt ice. Then we want to heat the water. Okay, so once again we use MC water, delta T. Okay, so still 0.184 kilograms. The mass hasn't changed. But now we use the specific heat of water because we're dealing with water. And the specific heat of water is much higher than the specific heat of ice. It's 4190 joules per kilogram Kelvin. What's our temperature change? Well, we started at 0. What do we need to get to? 100. So 100 degrees. Okay, we need to heat it up 100 degrees. All right, so you multiply those together, you get something big, like 77. Okay, so we've used this. So far we're at about 150 kilojoules, give or take. And then the last thing we need to do, going to make water into steam. Okay, so that's a phase change, and that's the latent heat of vaporization. All right, it's positive because we're adding heat still. So the mass is still the same. The latent heat of vaporization should be 22.6. And that gives us something giant. Apparently you need a lot of energy to make steam. 415.8 kilojoules. Okay, that's times 10 to the 3. Right, so and this is in thousands. And then if we want the total Q, Q1 plus Q2 plus Q3 plus Q4. So about 150 plus 415, that should be about 560, 575, 562. So that's the amount of energy you need to take very cold freezer ice and turn it into steam. Now why you want to do that, I'm not sure. You could just start with water at room temperature, but here you go. Although it turns out most of the energy comes from what? What step? Yeah, vaporization, right? The last step is the most energy costly. So actually, boiling water from ice is not that much more energy costly than just boiling room temperature water, because most of the energy just comes from here. Going from hot water to steam, it's a big jump. You need a lot of energy, which is why it takes so long to make tea. Sort of. Okay. All right, here's a question. All right. Mostly think B, although there's some strong holdouts for sticky. Please discuss and vote again. Just like that phrase. Always bad when your joke answer gets lots of votes. That would be funny. All right, another couple seconds. Make sure you voted again. Lost people already. Better. Was that just you? So there's more energy, right? Because you can see the difference in energy between very hot water at boiling and steam just after boiling. It's about 415 kilojoules. Okay, it takes a lot of energy to make steam, and that energy gets stored in the steam. All right, it's released if you take the steam back to water, and it's released on you as the water condenses on you. Okay, so all of that energy comes out as you put your hand in steam. So it's actually much worse to get burned by steam than it is to get burned by water, which led someone in the last class to ask, is that why people always scream in movies when somebody breaks a pipe and it sprays steam at them? And I guess the answer is yes, but that's not real. Okay. So anyway, the application for this is something called calorimetry, which is just a fancy way of saying conservation of energy for systems in thermal contact. Okay? Basically, if you have system A and system B and you put them in thermal contact, which basically just means touching, okay? And it's a fancy way of saying touching. Heat flows back and forth between the systems, and you could say QA, QB. Eventually, what do we reach? Thermal equilibrium. Everything is the same temperature at the end. I'll get to in a second. And what that means is any heat that goes from here to here, the negative version of that heat goes the other way. And when you sum up all the heats going back and forth, they should be 0. And that's conservation of energy still, okay? So blah, blah, all that jazz. And that's the end result. And it turns out you just need these things. So we basically only did one side of that equation. We only did one direction, right? If you wanted to talk about what was actually heating that stuff up, you'd say, like, we threw this in a big pot of water or something, or we threw a metal bar in there that actually melted the ice, okay? So it has to be 2 systems. This is just one isolated system. This is what happens when you have 2 systems in contact. Yes?
What is dry ice?
What is dry ice?
Yeah.
That's carbon dioxide. Oh, that's sublime. And you can get, I think that's still called the latent heat of vaporization. But it burns, yes. Yes, it does burn because it transfers heat out of you into the ice. That would be systems in thermal contact. One system is you, the other system is the dry ice, and they transfer equally, but it hurts. What? Well, ice and salt. What does the salt do? Yeah, it increases the temperature you need. Like, so it changes the freezing point of ice. Yeah, so you can make things colder. So, like for instance, why do we sprinkle? Well, we don't do that here. But let's say we lived someplace where it actually got cold. Like Michigan, that's a good choice. Why would you put ice on the sidewalk when it's ice? Why would you put salt on the sidewalk if it's icy? Yes.
It makes it more difficult for the water to form ice.
Yeah, it makes it more difficult for the water to freeze, right? And if the water doesn't freeze, then you don't have ice that you slip on and fall and either look stupid or actually hurt yourself. Okay. All right. Which are both good options. Do you guys want to do one of these problems? They're pretty easy. Okay guys, so this is a calorimetry problem, meaning we now, instead of having one system that we're calculating the heat in or out, we're calculating 2 different systems. And what are our 2 different systems in this case? Well, they're going to be ice and steam. All right, and the key to calorimetry is that when we add up all the heat that goes into the ice and all the heat that comes out of the steam and we add them together, we're going to get 0 because any heat that comes out of the steam must go into the ice because calorimetry just means basically it's trapped in a thermos, so anything that comes out of one thing has to go into the other thing because there's literally nowhere else for it to go. Now the key here is we want to find T final. So when it reaches equilibrium, we want to know what that equilibrium temperature is. In this case, we have, here's our 2 systems, right? We have 3.5 kilograms of ice at 0 degrees Celsius, and then we have 1 kilogram of steam at 100 degrees centigrade. Sorry. And of course, we might need to think about things in terms of Kelvin. So, oh no, but it's a difference. So we don't have to convert the degrees. So what we're going to do is we're going to calculate the heat transferred into the ice and the heat transferred out of the steam. What do you think we're going to get at the end? Well, unless your ice is a lot of ice that's really, really cold, or your steam is like an unbelievable amount of steam that's really, really hot, neither of which seems to be true since they're about the same amount, we're probably going to end up with water. And the like key here is what temperature is the water going to be. So first, we're going to figure out all the heat from the ice plus all the heat from the steam. And we know this has to equal 0, and we're going to solve for T final. All right, so here's this. This is all the stuff for Q for the steam, and this is all the stuff for Q for the ice. So for Q ice, we want heat transferred probably another R there, into ice, right? Because the ice isn't getting colder, so that means heat has to be going into it. Now Q ice is going to be equal to, there's first a phase transition, so the ice has to become water. So that's going to be M for the ice, times latent heat of fusion, because we're going from a solid to a liquid. And this will be positive since we're going from solid to liquid. That means you're adding heat into it. And then M ice, the melted ice has the same mass as the ice, so we can leave it like that. C water, and then T final minus T initial, that's our delta T. But remember, we're trying to solve for T final, so we want to write it like this. So this is just our stuff for ice, like this. Okay, we can plug in some numbers and it gives us something that looks like 3.5 kilograms times 3.33 times 10 to the fifth joules per kilogram plus 3.5 kilograms, 4190, this is C for ice, joules per kilogram Kelvin, T final minus 0 degrees Celsius. And we're going to leave this like this for now, and you'll see why. I'll come back to it. Then we're going to talk about the steam. So heat transferred out of steam. So that's going to be Q steam, which is we're going to have to go from steam to water, and then we're going to cool down the water. So this is going to be M steam, L vaporization, because remember, we're taking the heat from the steam out and giving it to the ice. So that's where the negative sign comes from. And then this is our first Q, right, just for steam. And then we have this other term where we're actually cooling down the water. So this is going to be M steam still, C H2O again, water, and then delta T, so this is going to be T final minus T initial, which in this case is 100 degrees Celsius. So we can plug in some numbers. We end up with -1 kilogram times 22.6 times 10 to the fifth joules per kilogram. And then this is going to be plus 1 kilogram, 4190 joules per kilogram Kelvin. And then T final minus 100 Kelvin. You're going to be like, why isn't that negative? But whatever T final is, we know it's going to be less than 100 because this can't get hotter without turning into steam. Okay, so this is our heat transferred out of the steam. And then we go back up to this idea. So we add all these together. So Q ice plus Q steam equals 0. And this just ends up being sort of an algebraic nightmare. But you just put these together, set them equal to 0. Okay, so 3.5 kilograms times 3.33 times 10 to the fifth plus 4190 T final plus -1 kilogram negative 22.6 times 10 to the fifth plus 4190 T final minus 100 equals 0. Algebra happens. And you should get your T final when you solve for T final, right? So here's your T final. You're going to distribute here and solve over here. You just do a bunch of algebra, which I'm not going to do right here, and T-final is going to give you something like 78.8 Celsius. Okay, you can also get this in Kelvin, but that's what you're going to end up with.